You want to really understand everything on this exam? Well, keep watching. What I suggest you do is pause the video whenever I come to a new question, so you can give it a go before I show you how I did it. Question 1. Okay, so to find out which one of these equations is true for all these points, we could just pick one of the points and see which equation works for it. So I might pick x equals z. Now that has an argument of 45 degrees, or pi on 4. So we could work out like x to the 7 if x is z. Well, we actually already have that on the diagram. It's down here. So that minus 1 or plus 1 isn't going to be equal to 0, so you can see that neither of those equations works. So let's work out z to the 8. That would have an argument of 8 times pi on 4, which is 2 pi. And it's got a modulus of 1, so that's going to be 2 pi is around here. So z to the 8 equals 1. And that makes this equation true. And if you just want to check, we could pick one of the other points as well, like we could try z cubed and see if that also satisfies that equation. So z cubed has an argument of 3 pi on 4. So if we do that to the power 8, so z cubed to the power 8, the argument of that would be 8 times 3 pi on 4, which makes 6 pi. So that's just 3 full revolutions. So 1, 2, 3, and we'd end up over there again. So that would also equal 1. So that satisfies that equation as well. Question 2. Okay, so this ratio between the distance from P to S and the distance to the line, that's actually just the eccentricity of a conic. We've got an eccentricity of a half. And that makes it an ellipse, if you know your eccentricities. But let's say you didn't know that, and we just want to visualize what's going on. So we've got this line, we've got a point S. So let's think of some points, some possible values of P that have distance from P to S half the perpendicular distance from P to L. So we could, for example, have a point there. So there's the distance from P to S, and the distance from P to L is twice as much. That would be one possibility. We could have something sort of maybe around there, where that distance is about half that. We could have a point up here. That would be another possible value of P, because that distance is half of the distance from there to there. We could find quite a few points, but you'll see that they all are sort of like this. So all of these points I'm drawing have this distance from P to S being half of the distance from P to L. And you can see that they form an ellipse. Question 3. So we could work this one out just by plugging in all these values for z and seeing if they work. So let's try A. If z is 1 plus root 3i, and we're subtracting 1 from that, then we get root 3i in that. And then the modulus of that is just root 3. So is root 3 between 2 and 3? No, root 3 is 1.7-ish, so it's not going to be that one. For B, we're going to get z minus 1 is going to be 3i, and then the modulus of that is just 3. So that isn't less than 3, it's equal to 3, so that one also doesn't work. We could try C. That would give z minus 1 is 1 plus I, and then the modulus of that is square root of 1 plus 1, so root 2, and that's about 1.4, so that doesn't work either, that's less than 2. If we try z equals 3 minus I, we get 2 minus I for z minus 1, and then the modulus of that is root 2 squared plus 1 squared, so that would be root 5, and that's going to be between 2 and 3, so it's going to be D. The other way that you could work it out is you could actually sort of picture what's going on there. Z minus 1, this thing kind of also means the distance between z and and 1. And that distance is between 2 and 3. So that actually gives us like a circle. Well, a ring, I guess, where you've got anything between a radius of 2 and 3 of distance from that point. And then you could kind of plot these if you wanted. So 1 plus root 3 is still, we want it to be inside this region. 1 plus root 3 is there. 1 plus 3i is going to be right there. So just on the edge, so that doesn't qualify because it's strictly less than. 2 plus I would be sort of there-ish, and 3 minus I will be there. So that's inside the region that we want. Question 4. Okay, so we've got these options for what this graph could be. And let's have a look at A and B because they're quite similar. Because if you solve this one, you'd get y equals plus or minus root f of x. So quite similar to A. The problem with those two is that where f of x is negative, this bit and this bit, that wouldn't have a solution for y. So these bits would just be like missing from the graph because you can't have square root of a negative number. If you're graphing real values, that is. And let's have a look at D. So f of x squared. The problem with that one is that that would mess with the x values. So you can see these, the zeros of the graph, where x equals 2, that would shift. So you wouldn't expect to have a 0 also at 2 here. It would actually be at root 2 if we were doing f of x squared. So it can't be D, it's got to be C. Question 5. Okay, it is possible to do this one by saying like alpha beta gamma equals -2 and alpha plus beta plus gamma equals 0 because that's the coefficient on the x squared and so on, and try to manipulate those equations until we get the value of alpha cubed plus beta cubed plus gamma cubed. But there is a much easier way, which is to think of it as like, so x cubed minus 2x plus 2 equals 0. That has the solutions x equals alpha, beta, and gamma. If we said let w equals x cubed, and then try to write this equation in terms of w instead, so it would be w minus, so I've replaced the x cubed with w. The x is cube root of w. Now, this equation has the solutions w equals alpha cubed, beta cubed, gamma cubed, because we know that if x equals alpha, that solves that equation. So w equals alpha cubed must solve this equation. So that means if I can turn this into like a standard cubic equation, then I can read alpha cubed plus beta cubed plus gamma cubed off the coefficient on the x squared. Well, the w squared, sorry. So what we want to do is take this equation, which has those solutions, and manipulate it until it turns into a standard cubic. So what you want to do there is get the cube root alone by itself on one side, and then we can cube both sides. So let's shift that over to the right, and then cube both sides. So this cubed will be w cubed plus 3 times w squared times 2. 3w times 2 squared plus the 2 cubed. And this cubed will be 8 times w. So let's simplify this. We've got w cubed plus 6w squared. That makes 12w, and let's shift the 8w over as well. So we've got plus 4w plus 8 equals 0. Okay, so this is now a cubic equation that has those roots. And that means that alpha cubed plus beta cubed plus gamma cubed is going to equal negative that coefficient. So that gives us B. Question 6. What we want to do here is sub in the z equals 2 plus I into this equation. and then we can solve that for a. So we'll need z cubed and z squared, so let's just work those out first. So that's 2 plus I times 2 plus I. You're going to get the 2 times 2 is 4. We're going to get a 2i and another 2i, so that'll make a 4i. And then there'll also be I times I, which is minus 1. So 3 plus 4i. And then let's also work out z cubed. So that'll be z squared times z. So we'll have 3 times 2 is 6. We'll have the 3 times the I, and also 4i times 2 is 8i. So 3i plus 8i is 11i. And also 4i times I will be negative 4. So 2 plus 11i. Okay, let's plug those values into there. So we've got the z cubed is 2 plus 11i. We've got a times the z squared, which is 3 plus 4i, minus 7 times the z, and plus 15 equals 0. And we just need to simplify this a bit. So 2 plus I plus 3a plus 4ai minus 14 minus 7i plus 15 equals 0. What we could do is just take the real parts. So we'll have 2 and a 3a minus 14 plus 15. That's all the real parts. So that's minus 14 plus 15 is 1, and then plus the 2 is 3. So we have 3 plus 3a. That has to equal 0. Or alternatively, you could take the imaginary parts, so the 11i, 4ai, and the minus 7i. Let's simplify the 11i minus 7i, that's 4i. And then we've got that one. That's also going to be equal to 0. And either one of those equations will give you a equals negative 1. It's good to do both just to check, because they should both give the same solution. So that makes it A. Question 7. If this one confuses you, it might be a good idea to actually just draw some odd and even functions. So we could pick just a parabola for f of x. And for g of x, I might just pick I could actually just do y equals x. So that's an odd function, and that's an even function. And you can split this up into two integrals. So let's work out what this one equals. So that's the area under the curve. If that's minus a, and that's a, it's all of this area underneath. And you can see that this area is the same as that area. So this is just going to be equal to twice the integral from 0 to a. So that whole area is twice that area. That's all that's saying. And for the g of x, if that's minus a and that's a, and remember that the area, when you're doing integrals, it's signed. So this area is negative and this area is positive. So when you combine them, they actually cancel each other out. And that whole thing is 0. So this integral just equals that. So that would be A. Question 8. Okay, let's have a look at the definition of odd and even functions. An odd function will have f of minus x is negative f of x, and an even function has f of minus x equals just f of x. So the way that I think about this is that an even function doesn't care whether x is negative or positive. It's the same result. So that will give you graphs that are symmetric about the y-axis, because the function doesn't care whether you've got a positive value of x or a negative value. It's going to be the same y value. And an odd function will give you a graph. So for example, x cubed has a graph like that. And that has not mirror symmetry, but rotational symmetry, where if I rotate this 180 degrees, we get the same thing. And you can see that by, if you just pick an x value, and that has a certain f of x. If I look at the minus x, so f of minus x will be the y value there, and you can see that that's the negative of this one. So that's how the graph relates to that definition. So let's have a look at the possible responses. So the idea is to plug in minus x and see if you get the same thing or do you get the negative of this. Let's try it out. If I plug in negative x, minus x squared is just x squared, and then cos of minus x is just cos x, because cos is an even function, that's its graph there. So we get the same thing when we plug in negative x. That's just equal to that. So that makes this one an even function. So that's not the answer. Let's try B. If we plug in negative x, then because it told us that f was odd, we know that that is negative f of x. And then this f is the same f, that's also odd, so we know that we can take that negative out the front. So for this one, we get the negative of the original thing, so that makes this one odd. So that'll be the answer, but just to make sure, let's check the others. So for C, we get f of minus x cubed times sine of minus x. That's f of negative x cubed. And then because f is odd, that'll be negative f of x cubed. And sine of negative x is negative sine x, because sine is an odd function as well, if you remember. Its graph is like that. So that's an odd one. Now these negatives will just cancel, and we're just left with the original one. So that one is an even function. So intuitively, f is odd and x cubed is odd. So if we do f of x cubed, that'll give an odd function. And this one is odd, but when we multiply odd times odd, the negatives cancel, so you get even. Let's have a look at D. So we'll plug in the minus x. That's just f of x squared. So when we plugged in the minus x, we got the same thing for that one. So that part is even. And we already know that part is odd. That's just, that negative will come out and cancel with that negative. Now this doesn't have much of a relationship with this one. Like it's neither of these things. It's not the negative of this, and it's not the same as this. So this one is neither odd nor even. So it's definitely B. Question 9. Okay, so we've got this circle. Has a radius of 4. And if dx by dt equals y, you can imagine if we're, let's say we're here on the circle, and y is positive here, so dx by dt is positive, meaning it's going sort of in that direction. That means it's going to be going clockwise. So we can rule out b and d. And then what we could do, we need to work out whether dy by dt is x or is it minus x. What we could do is differentiate this with respect to time. So you'd get 2x dx by dt plus 2y dy by dt. So I'm doing implicit differentiation here. If you haven't covered that yet, you might want to look that up. And then we can solve this for dy by dt. We know what dx by dt is, that's y. So this is 2xy, and let's shift that across. So we get 2y dy by dt equals negative 2xy. And then if we divide by the 2y, that's going to get rid of that, and we get dy by dt is negative x. So it's C. Question 10. So let's try to get an idea of what this inequality means by graphing f. So if I just pick some a and b, and maybe f of a is there, and f of b might be up there, then a plus b over 2 is the average of a and b, so that's the midpoint between them. And f of a plus f of b on 2 is halfway in between these two. And so it's saying that the y value at a plus b on 2, that's smaller than this. So it has to be below this point. So you can imagine how that's going to make a concave up function if it has to satisfy this. Because whatever 2 points we pick, the point in the middle has to be relatively low. And actually a good way to visualize where f of a plus f of b on 2 is to draw a straight line through those 2 points. And then that is f of a plus f of b on 2. So it has to be underneath that. So this is just the same as, basically the same as saying that f is concave up. Now let's see how that applies to the possible answers. So if we're doing the integral from 0 to 1 of f of x, where f of x has to be concave up, could be something like that. And that integral is the same as the area in here. So if we can try to think of that as an area, maybe we can figure out if this is true. So f of 0 is that height there, and f of 1 is that length. And so what we could do is think of this as the area of this trapezium, because that would be the height of the trapezium is 1, divide by 2, and then you've got the 2 lengths. So that gives you the area of that trapezium. And we can see that the trapezium is going to be bigger than the area under the curve if it's a concave up function, because this has to be lower than this. So it looks like B is going to be true. That one's definitely not true. What about C and D? Let's just make sure that those don't work. So it's saying that the derivative at 1 over 2 is positive or negative. Well, in this one that I've drawn, it's positive, but it could also be going like that. This would satisfy that inequality, but it has f prime of a half being negative. So it could be that or that, depending. We don't know. So it's definitely B. Okay, let me know in the comments if there was anything in this video that didn't make sense to you. And stay tuned, because in the next video I'm going to be going over question 11.